Hi guys, good morning. As you can see, I am back at my hometown. Just reached right now at around 9:30ish, 10. And yeah, here is the video of today's Leetcode problem. I know it's coming a bit late, but I could not help out. But yeah, let's see the problem. Largest color value in a directed graph. I swear it's one of the best problems of a particular data structure or algorithm, I should say. I will not name the algorithm at all in the entire problem. When we will actually see, okay, it is something which is being applied. After that, I'll show you, okay, its name is that algorithm. That's the reason. I have also hidden the heading of this problem itself. But yeah, let's see this problem and see what happens, what surprise comes for you. So basically the problem says that it's a directed graph of n colored nodes. So basically the nodes are just n nodes, but the nodes are colored right now. And yeah, one more thing, the people have said that I repeat a few things. I just repeat so that you know what is important, but yeah, I'll just try to repeat a less and just let me know if it is being applied or not. So yeah, and m edges is nothing but, okay, the graph has some nodes and some edges, n nodes and m edges, and the nodes are numbered from 0 to n-1. Pretty cool. We are also having a string called as colors. Basically the string called as colors, as an example, first example itself, we have the string a b a c a. So basically this a is nothing but the color of the node 0. So the index is actually the node and the a is actually the color. So it just says, if we just write down this string as 0, 1, 2, 3, 4, the indexes wise, then the index 0, which means the node 0 has the color A, the node 2 has the color A, the node 4 has the color A. Color is nothing but we can just say, okay, these have the same color, and we just name the color by A, B, C, so on and so forth. Just says node 1 has color B, node 3 has color C, and so on. As you can easily see in the example itself, it is the same. Node 1, node 0, node 2, and node 4. Node 0, node 2, node 4 have color A, which is the pinkish color. I also marked in the pink. Node 1 has the color B, which is in the purplish, baby purple, jubi, whatsoever. And node C is in the C color, which is, let's say, the blue color. It is just showing me the different colors of every node. Cool, pretty cool. Next thing says is a valid path in a graph is a sequence of nodes, which is, see, if you're not, if right now still you don't know about what is a path, what's a valid path, then I highly recommend to go and watch the second lecture of our BAP graph series, where every term we explain very deeply what's a path, what's a cycle, what's a cyclic path, and what's a cycle, and everything. So like it's a path, like I'll just repeat, path is nothing but, okay, if we have some edges between some nodes. If I say, okay, is there a path from 0 to 2 to 3? You will say yes, there is a path like this. But if I just ask you if there's a path directly from 0 to 3, no, right? We have to go via 2 to actually reach 3. So 0 2, 3 is a valid path, but 0, 3 is not a valid path. It is just saying the same thing. Next thing is, the color value of the path is the number of nodes that are colored the most frequent. What I mean by that is, for any path, as I said, this whole graph, it can have many paths, but I have to find out for every path, for every path, what is the color value of that path. So let's see what are, firstly, let's see what are paths can be there. One path is this, one path is this, one path is this, one path is this, right? Now, next path is this, next path is this. Now, next path is this. So I showed you all the paths. Now, what's the color value of a path is, if I choose this particular path, then the color value of this path is the color which is occurring the most frequent time, the number of times that most frequent color appears. So here, as you can easily see, that the red appears twice and a blue appears once. So this color value of this particular path is 2 because the red is appearing twice. The color value of this path is 1 because both red and purple occur once. The color value of this path is 2 as the red occurs the maximum number of times and the number is actually 2. The color value of this path is 3 as the red occurs 3 times and the blue occur 1 time. What's the maximum? 3. So the color value is 3. The color value of this path is 1 because both red and blue occur 1 times. The color value of this path is 2 because red occurs twice and blue occurs once. The color value of the path is 1 because red and blue both occur once. The maximum, what we need to return is the largest color value of any valid path. I showed the valid path. I showed the color value of all the paths. We need to return the largest color value, which means the largest color value of all the valid path is nothing but 3. That's the reason we have to return the largest color value of any path. So the answer is 3. And it's also saying that, okay, return -1 if the graph contains a cycle. For sure you won't be having a valid path in such a graph which they want to have. So whensoever your graph will have a cycle, you have to return -1. We will look at this condition in the last, but let's look at the main problem first. But you understand what means by cycle? It's just that, okay, if we start from a node, we can come back on the same node again. It's a cycle. So in this example also, it is saying, okay, if it's a cycle, you have to return -1. That is the problem so far. Now, first thing, you know for sure one thing, okay, what Aryan told was, I need to find all the valid paths, I need to find the color value of all the valid paths, and I need to return the maximum color value of whatsoever I found. Let's try the same thing. Why not to find all the valid paths? So if we look at the constraints, we have n nodes. If we were try to find all the valid paths, which means if I have a node right here, right here, right here, so I can have m edges, but the paths, it can be insane, right? Paths can be from here, 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 here. So it can be many paths. If I have go about for one node, just imagine for one node itself, in this example itself, from this node itself, from it's a very simple example, but from the here itself, I can have how many paths? 3 paths from here to here, from here to here, from here to here, from one node itself. Then if I just go on repeating from here to here, then here to here again, then if I just go on repeating from here, so it's kind of, and it's very simplified, it's just a straight path, and still it's n into n minus 1. I'm just saying it's a straight path and it's n into n minus 1. What if it is having multiple, let's say here, let's say one more node is here which is pointing to here, then it's pointing to here, then it's pointing to here, then it's pointing. So the path can be insanely large. So one thing for sure, I cannot find every path and find the color value of that path. That's not possible. If I cannot find the color value of every path and I want to find out actually what is the color value and what's the maximum color value, so can we see one thing in the example itself? See, ultimately my aim is to find the maximum color value, right? So for that reason I am going on every path. Is there any chance I can actually get the maximum color value by not iterating on every path possible? Is that possible? Let's look at the example again. If we go and look at the example again, when we have this path starting from A, one path which starting from node 0, one path possible is 0 to 2. Okay, that's one path. Another path that is possible is 0, 2, 3, 4. Another path. What do you think? If I have this path, the color value was 2. If I anyhow increase the number of nodes in this path, do you think the color value will anyway going to decrease? No, right? It's either going to remain same or it will increase, which means that when at the moment node 3 was added, it was a blue color, so still the color value was nothing but 2. But when the same color node, which means the node 4, which was of A color, it got added, the color value increased. So anyhow we get to know one thing: if the number of nodes are more, for sure the color value will be more. And again, I'll just show you another example. If you start from, let's say, node 2, then if you have this node, let's say 2 or 3, then the color value is 1. Next time when you add any node, let's say it would have been, let's say, node 5 with a color, let's say D, still the color value would have remained 1, but it would have never decreased. It would have only be same. It can be only same or it can increase, but it would never decrease. Thus, I can for sure say one thing: if I have some path, I'll just try to maximize the length of that path. It's for sure the color value will either remain same or will increase, which means that if now my whole task is up till one thing, earlier what I was trying to do was I was just trying every path possible. Now I will just try the limited paths. What path? I'll just try this one path, which is the longest path here, and I just try this one path, and I can just go on to this path and go on to this path and ultimately find. Now you saw what happened. Ultimately my problem reduced from so many paths to only one path right here and one path right here, which means the color value 1 and 3. Now let's see, were we able to actually reduce it? Which means that if I have the graph something like this, my paths which I need to actually see would nothing be one path right here. See already I have marked in the actual colors, so look at it once. After that I will just make it dirty. So one path right here which I have to actually look and see, one path right here for this node. I'm saying one path right here, as I showed you. Sorry, wrong color. Yeah, for this node right here, one path right here as I showed you. But as you can see, same for this end node, one path can also be from here. Thus you can see one thing also, although I am having the longest path, but still in this longest path also we can have multiple jiggling paths. Thus still one thing, if I just go on to find all these paths, still it can be many. Why? Because for this example itself, as you can see, right, let's say if it was there, and yeah, so for any node right here, let's say here also, and here also, any node right here, if I'm just going to here, then again I can just go from here, go from here to here, then go from here. So if we have many edges like this, so the paths, it can be multiple. So I'm just saying, okay, we have found, okay, what all paths I actually need to look at, but at these paths also I need to actually make sure that I'm not iterating on every node again and again for every path. Which means, if we look at this example again, then for this particular path I'm just moving at this node once, but for the same path as it is coming, for the same node as it is coming from a different path, still I will have to look at it. Understood? For the same node, again I'm going on it. For the same node, again there is one more path, so I'm again going on it. It's for sure I have to do such that I need to get to one node just once, because my n is nothing but, you can see, it's 25. So it's not possible for me to go on every path. I know the paths have become less, but still I can't go on every path possible, because still the paths can be many. That's how we will think, okay, now we saw, as we need to just go on it once, how about just use this particular node to actually transfer the information to all its child. Which means, rather than going on from here to here again and again to every path, rather than just start from a node, okay, what information you have, just spread that information to your childs. Then I'll just move on to the childs and I'll just ask him, okay, what information you have, just spread on them. Thus we can just simply, what's this spreading is called? It's just a BFS. So what we can do is we can just do a BFS. As I said, the paths, it can be overlapping, which means a path, it can be having like this, like this, like this. Thus I just have to do a simple BFS from every node. I'll just, okay, what information I want to grab? What information I want to grab? The color information. I just grab that color information from here. I'll just move it to its child, and the child will automatically take care. Okay, now I don't have to move or iterate on that particular node again and again. As you can easily see, if we look at this path, so for this particular node, it's in all the paths. So what I will do is I'll just go on to this node and I'll just provide its node information to all its child, and it will be done. One time, it's done. This is how we can do a BFS. But Aryan, is simple BFS enough? I mean, what a simple BFS does is, okay, if we are at the node, if 1, 3, 4, 1, 2, 3 are the parents and 4 its child, then as soon as you said that you want to visit every node once, so it's best to use a BFS. But in BFS, whensoever you visit the parent child, you just push the child. So as soon as you visit the parent node, you push its child in the queue itself, right? You do the same thing. Then when you actually go on to 2, you just see, okay, the 4 was visited, so you will not push that 4 again. It is what you do in a BFS. But as I said, in our problem, the paths, it can be many. It can be coming directly, it can be coming from various paths. So what I want to do is, I just want, okay, it should come by one path. Okay, it's one parent is there. Its information should be with me. What's the information is from 1, it should be with me. Okay, what's the information is from 4 and 5, it also should be with me. 4 and 5 also information. What information? The color information. I'll show the information, but it is what I'm thinking. Okay, I have to go in my graph deep and I can only visit my graph node once. So I thought to do a BFS, but a standard BFS, it actually means I have to go, and when I visit a node, I have to mark my child as visited and I have to push that child in the queue itself. But if I push the child in the queue without even asking other parents, maybe the other parents might have contributed better. What if they have contributed better? So why to push my child so early? I'll push my child only when all its parents are done, which means I'll just go and see 1, 2 and 3, because all these are parents of 4. I'll just go and ask, okay, what all you can contribute to your child, what all information you can give to your child. As soon as you give all of them, when you give, I'll just push my 4 into my queue. It is how this BFS is being modified. And now I'll tell you what this algorithm is called. This, how you push in your child when your all the parents are done. It is nothing but a topological sort. I never told you that we are going to apply a topological sort here. I just showed you why a modified BFS is required here, and that BFS is nothing but helps us to get a topological sort. If you have not seen what is the use case of topological sort, you can just go and watch the first lecture of our graph series, where we have actually told the use case of this topological sort. Why this is important. It's just how the dependencies work in our compilers, programs, operating systems, everything, IntelliJ, PyCharm, everywhere. This is how our dependencies work with this topological sort. But yeah, it's just an information, extra information for you. It's nowhere required that you should know topological sort for this problem. Nowhere required. I just showed you how your BFS will be modified. No way, if you don't know what's topological sort, you can stay on the video, because I never told you you want to know this thing. It is, I just told you that you have to modify your BFS such that when all the parents are done, only then I'll push my child into my queue. And Aryan, how to know when all my parents are done? I'll just have an in degree of every node. In degree was, if you don't know, then you can just go and watch lecture 2 of our bar graph series. It just says in degree is nothing but how many incoming edges are there, and incoming edges will say me how many parents are there. As soon as my in degree is being reduced, as soon as it becomes 0, which means all my parents are done, I am good to go to my queue. So I'll just use the in degree thing to actually move my child into my queue, which will actually show me, okay, in degree 0, which means all my parents are done. All the information which I need to have for my child, it's done. Okay. Now, you are very close to the problem. As we said, okay, we will actually push when my degree becomes 0. But as I said, I'll just have the longest path possible. So how to know from where to start itself? Right? I'll just say start from the top. But how to know, Aryan, what is the top? You said, okay, in the picture it can be visible. Okay, it's a top. But Aryan, how to know that it is the top? In a directed graph, how to know it is a top? I just say, okay, you can see that no one is above it. No one is above it, so it is the top. No one is above it, so it is the top. Okay, I'm repeating the same thing, but I'm not. If it is a top, which means the in degree is 0. In degree is 0. Thus, you can easily say, okay, to find the top, you will just grab all the nodes whose in degree is 0. So it will just say me, okay, all these are top. Why I'm saying all these are top? Because there can be multiple nodes with an in degree 0. My graph would start something like this, where all these are kind of tops, and then my graph starts. So my top can be 1 also and many also. So I'll just grab all of these nodes which are at the top and push it in my queue, so that I can start my BFS from these top nodes. It is what I'm gonna do in my actual BFS. Let's see that part of code very quickly. It's not the exact code. You have not seen the algorithm right now. It's just what you have seen right now. The part of the code is nothing but, firstly, just make that in degree thing. I told you why it is important. It is important firstly because you need to grab the number of parents, if it is done or not, completed or not, and for sure to actually also grab what is the top nodes of this particular graph. Okay, the standard way of making the graph, that's pretty sick. Then I just iterated on my edges. I just tried to make my graph from node U to node V, which means from node U to node V only, as it's a directed graph. Cool. I just also update the in degree as it is from node U to node V, which means the in degree of node V is being updated. In degree of node V, which is this part, is being plus one because one edge is to V. Then I just go on to I just have this queue for my standard BFS traversal. We need a queue, and this is a 0 degree queue, which will actually tell me at this point, okay, the elements which are in my queue have the 0 in degree. Cool. Then I'll just iterate on every node possible, and I just try to grab the top node. Top node is nothing but in degree 0. I just grab it and I'm push in my queue. Okay, my in degree part is done. But Aryan, you said that when the parents are being called and when we are about to push the child, I have to provide some information to the child, right? What information I have right now? And information was of color, right? Because for sure we are moving the colors to the child. I just wanted my color because I want a color value. Color value is nothing but the maximum number of colors in that path. Color count I want. Which means the parent needs to send the color count information to its child. And there can be many parents. And the color can be at max 26. Why? Because the alphabets are from A to Z. So for sure, one thing, oh, my screen goes blank. Just a quick thing, my screen went blank. Damn, why? Is it up? Yeah, it is. So now we can easily say, okay, we want that information. So for every node, as I will go down, that's what she said, I need to maintain the color value count of every color. Which means if for example, I choose example very specifically. Just look at the colors mentioned in this example. If I have orange, red, blue, white, orange, and blue, it is the node. I am here, let's say, it is my parent, and I am actually analyzing my parents to actually push in my child. What I'll do is, firstly, I need to have what? I need to have my node, what all color counts it has so far. So for a node, I want, okay, what is the color count? For a node, I want the color count. Color count are how many color can be possible? 26. For one node, 26 colors possible. For n nodes, n into 26 colors. That's the reason I'll just make a count as a 2D array, which will actually help me grab, okay, one node, 26 colors, node U 26 colors, node V 26 colors, and so on and so forth. And I'll just iterate and just update the count of every node, because at the first place in the beginning itself, node, like here this node will have the color blue. So I'll just update, okay, count of V of color blue is 1. Count of this U is nothing but the node number. It is different for every node because it is from 0 to n minus 1. Of this white, let's say it is 1. So it is just making up my count array, which will actually help me to actually figure out, okay, what is I want to get to my child. Okay, I'm very good with this count. But what was my aim? My aim was to get the maximum count of every color. As I move on to my child, I just want to update the maximum count of every color. Which means if I am standing at you, I'm just thinking, okay, I need to give information to my child. What information I have right now? I have the information of count, U is this node number, orange is the color. I will have the information, just remember, I will have the information for every node, the count of all the colors I have. For node U, orange color count so far is 1. As you can see, it is 1. For node U, the count of blue color so far is 1, because you can see as it is coming from top. So I'll just get white color. So the blue color count is 1. So far it is saying, okay, information I have right now is this information. Now I want to give this information to my child. What will the child do? It will just say, okay, count of V, which means at this node, orange count so far is nothing but 1. Because so far as you can see, orange count is nothing but 1. See, it will say count of V, which means at this node, blue color count is nothing but 1 plus 1. 1 is from top, but actually its color is also 1. Thus, I'll just add a 1 because its color is also 1. And the count of blue color will become 2. But as I said, before moving on to my child, okay, one parent is done. It is done. But still one parent was remaining. I need to update. I need to actually go on to this parent also. So there we go. His parent, it will say count of, for me, orange count is nothing but 2. Orange and orange. For me, the count of red is nothing but 1. Because one red is also, because it is at this point of time, the paths are here and here. So right now I have this information with me. I want to pass the information to my child. My child already had a orange count of 1, but I am actually bringing the orange count. He will say, I am bringing the actual orange count to 2 to you. So remove that 1 and take the maximum whatsoever you get. Earlier you had 1. But now I'm bringing you 2. So you grab the maximum whatsoever you get. I'm bringing 2, like have 2. So it will just say, okay, I will have 2, which is the maximum it gets from its parent. As you saw, it will just grab the maximum what it gets from its parent. Then it will have the blue count, which is actually the earlier count itself, which was 2 itself, and the red count, which it came from its parent. And that is how, when all the parents are done, it has the ultimate answer which it need to have. As you saw what happened, the count of orange, it changed because of the other parent. Thus, I needed all my parents to get sorted. After that, I can only push my node, which is the child node in my queue. And the same thing, like what we did, I just grab the maximum whatsoever I can have from my parents, which means the current value which I have. Because this current value, it is being updated every time. And also the value from my parent, if I have the same color, then I'll just increase the value by 1 and I'm good to go. Now you got everything is a problem to solve, but just one thing, very small thing remaining. It was also saying that, okay, you have to write -1 if it's a cyclic thing. How to know it's a cyclic thing? Aryan, it is just a directed graph. We are having a BFS. If you have known this, it's very standard. In a directed graph, if it's a BFS, You just know one thing, but I'll just actually show you how it is done. Still, the video is being long, but still I'm going to show you. It is nothing but if you have this directed graph, if you are at this node and you're just visiting your directed graph via a BFS, so if it is visited, then it is done, then you land onto this node right here. You were pushing your nodes when all the parents were visited, but for this node, what will you push in? Your one parent is gone. One parent is gone, but still the in degree is nothing but 1. And the worst part is every node of this particular cycle has in degree 1. And no way it's gonna be 0, because everyone has some back and all are back of each other. So no way this can go, the in degree of any node in this, it will go to 0, which means no node out of them will actually move to the queue, which means the BFS will actually never happen at this particular cycle itself, which means all these will never get visited in my BFS traversal. As I said, it will never get visited in my BFS traversal. So why not just grab that visited count so far you have while doing the BFS? If that ultimately after doing the complete BFS, because how we know the BFS is complete? While queue is not empty, we do the BFS. As the queue becomes empty, my BFS is done. But ultimately I know all these were never in the BFS. So my visited count, which means the number of nodes which were visited while doing a BFS, if it is n, which means all my nodes were visited. But if it is not an n, sorry, some nodes were missing. Why they were missing? Because for sure all were them in a cycle. Thus I can just easily maintain a count of visited. I just update my visited as I go on in my BFS. Ultimately, and the last I'll check. If my visited count is n, I can return whatsoever max count I have so far. Max count is nothing but color, remember? Yeah, that thing. And if it is not visited, which means if my all nodes are not visited, I have to return a -1 because I could not complete my whole BFS. It's the same thing which you have to do. That's all. Entirely that's all. You covered edge cases, which is -1, and you covered how your parents is giving the information to the child and why they have to give, because you want to do it in O of n. That was pretty much it. Let's go to the quick code pretty quickly. It's exactly the same as I showed you. It's the whole thing. I was just explaining every code snippet as I was moving along in the code. So it is exactly same what we saw above, that we are making the graph, we are grabbing the in degree and pushing it in my queue, and we are also updating the count of every node color value to actually 1, because currently they have one color so far with them. Now actually the main crux was starting in this also small spread having explained earlier to you guys, but I'll still start from scratch. That okay, we'll have the maximum count which we need to return. You will have the visited. Why visited? Because ultimately you also need to return if it is -1 or not by saying if it is count is n, visited number is n, you have visited every array in my BFS. I just go on my BFS, which means until my queue is not empty, I just grab the top element of my, which means the front element of my queue. It's actually how a BFS will work. I'll just say, okay, one element is being grabbed, it is visited. Cool, it is visited. I just go on to all its child, which means all its neighbors, because it is being visited as a tree, so it is all its child. Then I just go on to every color. As I said, any node, it should have covered every 26 colors. It means from A to Z. Then I just update this maximum count value. I showed you why. Then I just say, okay, from this particular node U, I was just going to V, right? So one node for V is finished. So I just decrease the in degree of V by 1. One parent is done. I just do the in degree by 1. If I said all the parents are finished, which means my in degree of this particular node V, it becomes 0. It is good to push in my queue. I'll just push that in my queue. Lastly, when my all the childs are done, I can just say, or I can just put this condition above also. It doesn't matter. I'll just update my max count by actually all the colors information. Okay, for this particular node, what all colors maximum count I could have, because what I wanted was, I wanted nothing but, I'll just show quickly, I wanted my color value to be largest. So for one node, color value so far is nothing but the maximum of the color count I have for this particular node is the color value of that node. So I'll just say, okay, the color value of node u, is nothing but this, and I need to update the color value of every node. So I'll just go on in every node and I just keep updating the color value for every node, and it will just go on increasing, because ultimately I just wanted a color value which is maximum. Ultimately I just return max count if my visitor of n is, my visitor is equal to n, else I'll just go under -1. And as I told you that was nothing but a topological sort. Time complexity is nothing but a simple v plus e. V, as I said, if all the edges of all the nodes are just discrete edges, if nothing but we have the edges. It's very standard as BFS complexity. And space is nothing but we are making a graph, we are using a in degree array, we are using a visited array, we are also making a count array, which is v into 26. As I told you, for every node you are just grabbing this count, where it gone, yeah, n into 26. That's the reason you have this time complexity, and all the code in C++, Java and Python is just below. I hope that you guys liked it. If yes, then do the like button. I know the video has gone pretty long, but I wanted to show you the complete intuition of how you never know what a topological sort is, but still you were able to figure out an algorithm by just a standard traversal, which is a BFS, and you are good to go. I hope that you guys liked it. If yes, then do the like button. It helps me a lot. And just let me know if I just repeated a few things which were not required. I'll try to reduce them. But I just tried to repeat only those which are actually necessary for you to actually grab. Okay, it's necessary and you should hear it twice. But yeah, maybe I just spoke it. So if just let me know, it will be very helpful. And see you in another day. Goodbye. Take care.